Hi, everyone. As you're joining, we're just going to wait one more minute to allow everybody to come to the main webinar from the waiting room, and then we'll get started. Okay, I think we can get started. Thank you, everyone, for coming today, and welcome to today's webinar. Today's session is the second in our new series, our spring series, Advanced EHT Data Analysis. It's great that you can join us in real time, but if there are webinars you miss and you want to go back or just simply go back to and watch again, I want to remind you that all previous webinars are on YouTube under the Black Hole PIRE Science channel, so you're welcome to view them at any time. You can also see all the upcoming topics, dates, registration links at the Black Hole PIRE website. Hopefully the fact that you're here means that you've visited the website and you're familiar with the process. Both the website and the YouTube Science channel are going to be on the chat shortly, so you can always use those as well. Our webinar will last 1 hour, including time for questions, but if the discussion is continuing, we can go over a little bit. And as Dr. Stair starts talking, I encourage everybody to turn off their audio to avoid any background noise while we have the talk. You can ask questions in two ways. You can put it in the Q&A in the webinar, or you can put it on the chat, and I will make sure that we go through them at the end of the webinar. If you have clarification questions, I can also ask them during the talk itself. So with that, it is my absolute pleasure to introduce today's speaker, Dr. Ingrid Stairs. Ingrid is an expert on observations of radio pulsars and their companions. She studies binary pulsar evolution and is also an expert on using them for tests of general relativity. She's also worked on pulsar instrumentation and polarimetry and high frequency observations. She is a member of the NanoGrav collaboration, which is the North American Gravitational Wave Search collaboration that uses the Green Bank telescope, which you can see behind her right now as her background, and until recently also the Arecibo, but I am sure the collaboration is also is going to continue doing the fantastic work that they've been doing with other opportunities. So today she's going to tell us about time domain methods, how to detect mostly periodic signals in the data. And with that, I will turn it over to you, Ingrid.
Yeah, thanks, Mariel, and thanks for inviting me to give this talk. So the picture behind me was taken from the top of the Green Bank telescope many years ago now, but I thought it made a nice background. And the data that I've got on the slide here actually comes from the GBT, something I took for one of my projects a month or so ago, and quickly analyzed in time for the proposal deadline a couple of weeks ago. So I had it handy and thought I could use it to do some examples. So a lot of what I'm going to talk about today involves going from this kind of stuff to something that looks like that, with a nice signal that incorporates, all of the coherent information that is actually there. It's hiding somewhere in there. Actually, not quite in this version of the data, but we'll see how that goes. I will get into a few other techniques as well, what you do for some high energy signals and you know, non-uniformly sampled signals and things like that. But I'll just start off with the, you know, how we identify periodic signals. And sometimes it's pretty easy. This is the first confirmed extrasolar planet around Pulsar 1257 plus 12, famous observations by Volshan and Frail. And these are the pulsar timing residuals. So if you fit constant period and 1 period derivative, and the best you can do for astrometry, which Dale Frail got with the VLA, then you're left with this sort of very clear signature in here. And there's not 1, but 2, in fact, 3 periods in there, although 2 were visible at the time. So this kind of jumped out, right? I think my 7-year-olds could probably draw 2 curves that add up to that. But, you know, they might get the errors wrong a little bit, right? Here we have another example from the Kepler satellite, looking at transits, and it's clear that there are multiple transiting exoplanets here, a couple of gaps in the data as well, probably, but you know, you can identify sort of the same things showing up at the same period here and there, and if you do a careful analysis, you can split everything apart. But my point is, you can just look at this and see that there's something there. More often, we're looking at something like what I had on my title slide, right? This is, as I said, GBT data on a pulsar that is actually quite bright. Or you've got something where you've got a signal every now and then, like these red and green dots here, even though you've been observing the thing fairly steadily. And so well, those are the times we didn't get good data. The times with data are up here. So this is you know, a different case, and in this case we were able to discern a periodicity here as well, not something any of us was expecting. So there's a brief outline of the talk. I'm going to talk mostly about searching for radio pulsars, because that is really one of my areas of expertise, and all the different things that you have to consider, with a bonus consideration before we even get started. Then I'll talk a little bit about sort of sparsely sampled data, like that repeating fast radio burst we just had, and a few things that can also be used. And I'll finish up by talking about taking advantage of the periodicity of the radio pulsar signal to do the template matching, which leads to all of the high precision timing that we're able to do, for example, in the nanograph project. So a few considerations there, you know, using the fact that you have a periodic signal, but having to build up the template in a rather careful way. So if we're trying to find radio pulsar, we get a bunch of data from the radio telescope, and we're looking for, you know, a pulse signal, something that repeats, right? So right away, you can imagine that we're going to be using Fourier transforms, and we will, but there are other considerations. So one of them is a dispersive sweep of the signal across the observing bandpass. So here is an example with an observing band across 32 megahertz centered at 436 megahertz in the frequency domain. And you can see there are many little channels here, and the signal shows up in each one of those channels, but there's a shift from channel to channel. That shift is called the dispersion, and the amount of the shift is related to the dispersion measure quantity, and that's something we don't know a priori. So we have to search for that. We have to search for periodicity, and in many cases we want to check to see if there are any accelerated signals with a changing periodicity over the course of the observation. Here's an example with an hour-long observation of a pulsar in quite a relativistic binary. This is one of the white dwarf companion, and if this is, you know, every line here representing one sub-integration, so about a minute of data, the curvature here shows that the frequency is changing over time. So that's acceleration. We have to look for that as well. That takes a few CPU cycles, as you might imagine. So let's talk a little bit about that dispersion issues, because this shows up not just for pulsars, but also for fast radio bursts. So here's the same pulsar we had on the previous slide. This is the Vela pulsar at Parkes. And as I said, every channel is shifted relative to the others. But we know what that shift is, or at least we know what the dependence is. It is a 1 over frequency squared dependence. And here I've got the time delay relative to infinite frequency. And it's related to, as I said, 1 over frequency squared and this quantity called the dispersion measure, or the DM. So this is basically, I'll write it out here. The DM is basically the integral of the electron density along the line of sight to the pulsar. Exactly what the constant is here is a subject of some minute debate or arguing about conventions, let's say, within the community. But this is the standard definition that most of us use. So here is an example of dispersion, again, applied to a fast radio burst. This was the initial fast radio burst discovery, and you can see the long sweep here. And you can see the curvature quite clearly here, right? It's not just a straight line. So this is going from about 1.2 to 1.5 gigahertz, so somewhat higher frequency than over here. Same property. So we have to search for that. Because of the need to do that, we have to divide any observing band that we use into many, many small channels, right? That's what is shown here with the Vela pulsar fairly clearly, many, many little channels. The same thing has happened here, right? So typically hundreds of channels across an observing bandwidth of, say, a couple of 100 megahertz, depending on your center frequency. So in each of these channels, we then take the signal, which has been filtered, as a coherent signal, whether you're using, analog, actual physical filters, or doing this, in the digital domain. It's filtered as a coherent signal, but we want to detect it, so multiply it by itself to get the total power in that channel. Once that has happened, we sample it. And the sample rate we're going to call delta T here, and that's typically tens of microseconds for modern searches. Historically, it was a slower sample rate for many things, but the data I showed you was sampled at about 10 microseconds. And for big search, we would typically try to keep it at about 60 or 80 microseconds, something like that, so that we retain good sensitivity to millisecond signals. And then we have the total length of the observation, which we're going to denote by big T. And we write that in seconds. Different telescopes will use different things. The Parkes multi-beam survey used 3,500 seconds, a good long time. No, 20. Sorry, it was just over half an hour. 35 minutes is what I'm thinking of, but a good long time. So 2,100 seconds kind of thing. More typical observations are, say, 3 to 5 minutes, so a few hundred seconds, but still pretty long. As you can imagine, if you do a big survey like the P alpha survey that recently finished at Arecibo, or was forced to finish because of the demise of the telescope, that got more than a petabyte of data from the data that we did collect. So it's not super huge by today's standards, and I know the EHT project deals with large quantities of data also, but it's a non-negligible data storage problem and also processing problem. So we should ask, before we get started, what frequencies are we actually sensitive to in the data? So we have a long data span of time t, and it's divided into samples of duration delta little t. So we're going to call the total number of samples n. That, of course, is true for every frequency channel. Of course, this is real data and not complex, but we're going to do things in the Fourier domain mostly. So that naturally brings in the idea of using complex numbers. So usually the way we do things is to, once we have the Fourier transform, just write things in terms of n over 2 frequency bins and keep the amplitude and phase in each bin to do a very rigorous job, or just look at the power in each bin. There are different algorithms that do different things. So each frequency bin, once you've taken the Fourier transform, will have width of 1 over t. So the highest frequency that we can hope to see with this regular sampling is the total number of samples so the total number of frequency bins here times the width of the frequency bin, 1 over t, which results in 1 over 2 delta t. So this is what we call the Nyquist frequency. So it's set by the sample rate. You may have met this idea before. I'll just do a little sketch to illustrate what I mean by this. So if you have a sine wave, which I hope I can draw reasonably well. So that's the sine wave that we've got. If we sample it here, 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 etc., then we are getting full information about the amplitude of the sine wave. Now, of course, if your phase is wrong, then that's another story. But let's just imagine we're sampling, right at the peaks and troughs of the sine wave. We know exactly what that sine wave is doing then. So this sampling at twice the frequency of the highest frequency signal in the data will give you full information about that signal. Now, this is getting ahead of myself a little bit, but if we imagined a faster signal, let's draw something like this here. At the same sample times, this is a little bit ugly looking now. You'd have a signal there, no, there, sorry, a little bit off here. But the point is, you could draw something through here that kind of looked like that. It looks like a much lower frequency sine wave, even though the red one's actually going at a faster rate. This is what we call aliasing, where a signal that is actually outside the band that's sensitive to comes into your band at a wrong frequency. It's related to its true frequency by addition or subtraction from the Nyquist frequency, depending on your perspective, or actually double the Nyquist frequency. But it can be a problem, right? So you have to make sure that you can try to get rid of anything above the Nyquist frequency, whether that's in a hardware filter or through software windowing or filtering. And just be cognizant that, under some circumstances, you can have these aliasing signals come in, even though you're trying to avoid them. So let's say we have some data and we've got something like this, and we want to try different dispersion measures and periods. So imagine this is broken up into many frequency channels. Yeah, but no, we can't get started right away. This is the little thing that we have to do first, and that is getting rid of radio frequency interference. So call this RFI, because takes too long to say radio frequency interference. So RFI has many forms and many causes, right? The spark plugs from cars can be an issue. Obviously, your cell phone can be a big problem. Computers, if you're at an observatory, there are lots of places that force laptops to be inside a shielded room, for example. The DRAO, where Chime insists on that, for example. So there are a lot of different types of RFI. Satellites are increasingly becoming a problem. Starlink is going to be a real bear, by the way. So you want to find RFI and basically zap it out of your signal. Basically either zero it out or replace it with the local mean or median of the data. There are a few different things you can try to do. But there are lots of codes out there to do this. You can inspect by eye to see which channels are chronically bad, or you can run something like this RFI find routine, which is in this Presto code, which we use for a lot of pulsar search analysis. So this is Scott Ransom's code available here. He's got a great tutorial for how to use it all. So I suggest you download that and take a look at it if you're interested. So here's an example of this data, a little bit longer chunk of data than exactly what I've got here, but more or less this data, going up to 200 seconds. And the RFI find algorithm goes through and looks for things that stick up above the median, or stick up above more than a few sigma above the median in different ways, and comes up with a mask to be applied to the data. So it's finding things that have excessive power in them, where the RMS is larger than it should be, things here where the mean go bad. And it says you should really zap out all of those things. So the question is, does it actually help? So if we take this data set, not zapping anything, collapse all the frequency channels down, assuming a dispersion measure of 0, then take a Fourier transform, well, I've got a couple of different views of that Fourier transform here. We've got frequency on this axis here. You can see there's a lot of junk here that kind of looks like a bit of a comb. There's some actual little noisy stuff down here, which is potentially interesting data, but we can't get at it because of all this stuff. If you zoom in on this region here, you can see that each of these peaks has a lot of structure in it as well. So this is quite a mess. Now, if you do apply that mask, and then again collapse the remaining channels down to 0, it zaps out a bunch of data. But if you look at the couple of different views of the Fourier transform again, you see something that just basically looks like noise and is a lot easier to work with. So wear your mask, whether you're data or a human being. So let's say we've got that under control, and we want to try to look at the different possible dispersion measures now. So, we've got all of this channelized data, and we know the pulsar signal is going to make a sweep through that data following the 1/f² law. But we don't know what that is a priori. So the only way to deal with this really is to try to use many different DMs, make a whole bunch of time series with different amounts of dispersion sweep in them. Now, this could be a very inefficient problem if you add things up over and over and over again. So Joe Taylor, way back in the 1970s, came up with this tree algorithm, which owes a little bit an idea to things like the fast Fourier transform, where you skip doing redundant additions. And so you take, you've got 4 channels here, and you add up together, the sample going straight down, 1 across, straight down, 1 across. And here you make further combinations, adding in 3 and 4. This one goes straight down, this one has a small dispersion, and so on. And this one is basically linear down. So 4 channels will give you 4 allowable dispersion measures to search this way. Doing this procedure gives you an n log n algorithm instead of an n² algorithm, so it goes a lot faster. And we still mostly use this today. I mean, we're even using it in our Chime telescope fast radio burst searching. It's a slightly adapted version of the tree algorithm, which is called Bonsai because it's small and efficient. And that was developed by Kendrick Smith. So here he's showing what the additions of steps looks like for different values of the dispersion in frequency squared space. There is another fairly good algorithm out there in the last few years. So this is the fast dispersion measure transform. And the reference is here, and I missed out a parenthesis, sorry. Put that in by hand. So the idea here is that you're sort of computing many different dispersion measures at once. Here is the actual sweeping signal, and you're computing the signal strength if you look at start time, or end time of the signal in this case, and the length of the sweep, which is on this axis here. So that you get a strong peak in the signal here at the 50 millisecond dispersive time across the band, ending at 92 milliseconds, and you don't get signal in other places. It's all effectively equivalent. We decided to go with Bonsai in part because at the time we were evaluating things, it seemed faster, but this is an equally good method here, the FDMT. Okay.
Ingrid, may I interrupt for just 1 second? There was a question in the Q&A regarding the discussion of the RFI.
Yes.
When you said zapping, could you clarify what you meant? Was it getting rid of channels affected by RFI or something else?
Well, that, and also looking for broadband interference that might show up for a short time. If we go back here, over to the unmasked data, if you look through here, we've got the average and standard deviation of the data here. You can see that the standard deviation, for example, gets bigger here. So something is happening to the data as a whole. And that is a point that gets identified as needing to be masked out entirely. So the whole bandpass suffered from, an excess of noise for a little while there. So that's some of what we mean. At the same time, there can be channels that chronically have interference in them, and those would be here with the vertical lines in them. So it's a mixture of both things. We tend to use the term zapping sort of rather cavalierly to refer to all of this stuff together.
Great, thank you.
Okay, so yeah. At this point, we've got our zapped data, and we've done a bunch of dispersion measure trials. In this case, this is a pulsar that I know about, so I know the right dispersion measure to look at. And that happens to be 157 parsecs per centimeter cubed. Those are the units we use for DM. That's just what it is. So if we take a fast Fourier transform of that, we get a signal that looks like this. Now, I will say that in real life, when you have a much fainter signal and you don't know what you're looking for, one thing you really want to do is sort of detrend the data, whether it's here or in the frequency domain, sort of taking out a lot of the red noise, because that's going to really cause lots of spurious signal at low frequencies that can mess up your detection of any long period pulsars. So I've skipped that step here because I wanted to get straight to the fun stuff with the Fourier transform, but you should be aware that that's something that needs to happen in general. So again, a couple of views of the spectrum, and you can see there's a lot of nice stuff poking up above the noise here. And if we zoom in to the bottom, say 40-ish hertz, you can see that these spikes have very regular spacing, and they're spaced about 2.5 hertz apart. The period of this pulsar is actually 0.405 seconds, 405 and a little bit, right, which fits in with the 2.5 hertz spacing. So in other words, this pulsar has a lot of harmonics in its spectrum, and that's something we can take advantage of in pulsar searching. I'll show you how we do that in a moment, but in this case, that 2.5 hertz, we can fold the data at that frequency. So basically we take our time series and we wrap it around. So we go for the first little chunk of data, and we hit the 2.5 seconds, we go back to the beginning and stack it onto the first bit. We go back and forth like that, adding up all of the data coherently, building up the signal strength. And once you do that, this is again on the masked data, then you see you can build up to a very, very nice, well-defined sharp peak there. And this is a little bit of extra information where the Presto code does a little search to see what the best period and period derivative might be in the space of the parameters here. So what I want you to get out of this is that this pulsar has a very, very narrow profile, right? And that fits in with the sheer number of harmonics that showed up on the previous page here. If you look there, you've got harmonics going up to number 100 or something like that. So there's a lot of structure in the harmonics, and that's going to result in a very narrow pulse profile. So that's something we can take advantage of in searching, because most pulsars don't stick up beautifully like that, right? If everything were that easy still, we'd be finding pulsars every day without having to go through a whole lot of computing. But most of them are really buried down in the noise, and you can only see them, getting up to, say, 10 or 12 sigma or something like that, with some effort. But one of the things that we can do is to sum up those harmonics. So we just talked about folding the actual data on itself. The harmonic summing that we do in searching is kind of similar. So again, I'm going to try to sketch that. If you have a spectrum here, so this is frequency there, and this is your power intensity, you've got some kind of noise going on there. You want to take that same spectrum And then you want to take the first chunk of it here and stretch it out so that you're adding it sort of on top there. And this is going to build up to some combined signal, right, which now incorporates a couple of harmonics stacked on top of each other. And you can do this over and over again, realistically getting to about 16 or 32 harmonics is about as far as you want to go, both computationally and diminishing returns. But it really does help to build up a signal where you might have a lot of structure in harmonics, but maybe not so much in the fundamental, or maybe just low signal to noise overall. If you get to very wide profiles, as you can see, this plot shows the quality of the harmonic sensitivity here as a function of the fractional full width half maximum. At some point, it stops being useful, right? When you get out to pulse widths of about 0.3 of the entire pulse phase, the harmonic summing doesn't win you anything anymore, which makes sense because you mostly just got the fundamental in there at that point. So you're adding noise from there on. So another interesting thing happens when the pulsar's frequency maybe doesn't land right in the center of one of those big n/2 bins that you have. And that will also reduce your sensitivity. So another trick that we do in pulsar searching is to sort of interpolate between two neighboring bins to try to recover some of that signal. This is one place to look for how to do that. But if you didn't do that kind of thing, then at the offset halfway between two frequency bins, you'd be down in sensitivity by about 0.6 of your original sensitivity. Here you can make it so that you only lose less than 10% of the sensitivity, and this is just by, as I said, basically interpolating between two neighboring bins. That doesn't take too much time either, so it's a good thing. If we look at acceleration searching now, remember we had that curvature in the pulse phase versus time plot, which showed acceleration. So we'd like to maintain sensitivity to that. I mean, one of my favorite things is relativistic binaries with short orbital periods. So those are going to have a significant acceleration over any reasonable observation length. So we need to look for period derivatives in some way, or frequency derivatives, if you'd rather. So one of the ways that we've historically done this is just to take a long time span. This is from the Parkes multi-beam survey. So it was a 35-minute observation. We split it into 16 segments, did an FFT on each of those segments, and then stacked those with many different trial shifts to allow for different values of acceleration. So here's a small acceleration, here's a bigger one. Right? Oh, okay, no, this is a frequency and 2 times the frequency, sorry. But yeah, it works out to the same net acceleration in this case, my mistake. So this is a stack search, as we call it, or stack and slide, you might see it named also. This is pretty cheap computationally. You're doing a bunch of short FFTs instead of one long one. So that sort of compensates for having to do many different trial accelerations. But you're adding the power from each of these FFTs incoherently. So your sensitivity is reduced from what it could be in a fully coherent search where you actually maintain the phase information between the different segments that you're looking at. So you can do better with a coherent acceleration search method. And I've just got a bit of a laundry list here. There isn't time to go into all of those. But fundamentally, they all kind of end up using the same kind of information, except for this one down here. But one thing you can do is take the time series that you have and resample it to allow for different accelerations, right? So again, you're doing kind of an interpolation between successive bins to allow that to happen. An equivalent thing can be done in the frequency domain. And this is another one of Scott's things, where you basically build a template representing different accelerations and look for signals in neighboring bins that match up with that template. And you can declare what the acceleration is based on the peak then. You can also, in a different Scott ransom kind of search, look for phase modulation searches. So if you have a case where the orbital period of the pulsar binary is much less than your observation length, Like say you look at a globular cluster for 4 hours and you've got a 15-minute binary in there. The frequency there is going to map out, it's going to sort of go back and forth over the course of that 4-hour orbit many different times. And so that's going to produce a very clear expected shape again. So this is another template matching kind of idea in a way. And so that can be fairly efficient. There aren't too many things that seem to fall into that category, but in principle, this is a good thing to do. The last one down here is a dynamic power spectrum search. So again, kind of taking the stack slide method, as in you're doing segmented things, but you're looking you're looking sort of at for example, the grayscale of the brightness of the signal at different times and just seeing if something can pop out that way. This kind of thing doesn't sound like it would be terribly useful, but it is, because it covers or can cover the sort of intermediate zone between long period binaries compared to the observation time and really short period binaries compared to the observation time. So there's a reason to do this sometimes, although it's not in super common use. One thing I do want to talk about a little bit is what we're actually sensitive to, or what it makes sense to think that we're finding. I mean, if you're just looking at random data looking for spikes, you might want to say, oh, this thing's above 3 sigma. Let's go take a look at that in more detail, right? Not the best plan in this case, right? You've taken one data set and you have de-dispersed it many different ways. You've got the Fourier amplitude search with the large number of bins in it. And then you might be doing acceleration searches on top of it. So there can be a large number of trials here. And what that's going to do is mean that there's actually a large number of things that could pop up at what would normally, I suppose, be considered an interesting signal to noise ratio. So I'm going to just put this down here without demonstration. A good place to look is the Lorimer and Kramer Handbook of Pulsar Astronomy. But basically the number of trials that you're doing with the data, so the number of separate analyses of the same data set comes into it, along with some constants. And so it turns out that the minimum interesting signal to noise ratio is about 8. So really you only start looking at things once you get to about that level. And even then you get tons and tons of candidates produced, especially if there's RFI that's sneaking through and showing up as candidates. So you still need a human then to go through candidates. We often nowadays have a machine learning algorithm in there to do even more down selecting, get rid of RFI before a human looks at it. But there's still a fair number of candidates for a human to go through in general. I'll just mention another technique that's used for pulsar searching when you get to very, very slow pulsars and where that red noise can really hurt you. And a good technique, which is now quite well weathered, but still very, very useful, is the fast folding algorithm. So kind of like the FFT and the tree, you're avoiding duplicate sums. So it's an n log n process, and you can go look up the math for it. And that can find very long, slow pulsars. I can also find somewhat faster pulsars that are weak, but that have lots of harmonics. It can actually do better than the FFT search in some cases that are sort of not super fast spinning, but somewhat faster than what you might expect where you would need to use this low frequency search. So here's an example from the P alpha survey with a pulsar that was discovered in that survey. It shows you the power spectrum here, and you can pick out what the period is. Well, yeah, the periodogram, I guess, is a better thing to call it. And this technique gets used in exoplanet transit searches as well. So I'd like to spend a little bit of time on what you can do when you don't have such densely sampled data. Right? So, for example, if you look at X-ray data, you have photon detections. Right here is counts per second. This is a fairly old bit of data in this case, but from the NASA public outreach site actually, but I thought it was quite effective. So, you know, you're sort of at the mercy of when the photons hit or when you have an event happening. Right? So again, if you look at this, you can see there seems to be some periodicity here. You can probably take a fairly good guess by eye, actually. But the panels here demonstrate what you can get by doing epoch folding, which is a lot like what I talked about with folding the pulsar signals. You go through the first bit of data. When you reach the end of the period that you're testing, you go back and stack the signal on top of itself and go back, and go back, and go back, and so on. So you're stacking up the data at a bunch of different trial periods. So here's an example of a 10.5 day period where there's, you know, looks like a flat signal. Here's a 16.6 day period, which does match up pretty well with the actual physical period in Circinus X1. Right, so this is sort of the classic tried and true technique here in X-rays. You can do a bit better by making this a Bayesian argument instead. So the classic paper here is Gregory Laredo in 1992. I'm giving you lots of old papers here, but you know, the point is people have been thinking about these problems for a long time, even though there's still some room for improvement. So here is ROSAT data on a pulsar, which shows up in X-rays as well. And this is the basically the PDF that you would get from just doing epoch folding here versus the Bayesian analysis, which is effectively doing something like a Bayes factor, although they don't call it that in this paper at that point. But it allows for a better estimate of the period, or a more precise value. Whether it's accurate or not, of course, remains to be seen, right? But in principle, it allows for higher precision to do things this way. There are various other algorithms you can use as well, which are different ways of comparing something like a periodogram test, or in this case, harmonic summing, incoherent harmonic summing, comparing those to a flat distribution, just to check for how much you believe that the period is real. So a lot of things are like that in X-rays. We get unevenly sampled data in radios and obviously exoplanet searches, things like that as well. So here's an example from one of my old papers. This is a pulsar we, at the time, thought was precessing. We don't think that anymore, but the interesting stuff going on is still there. So usually with a pulsar, when you have a good ephemeris for it, you have flat so-called residuals, which are the data minus the best fit model to it. And those would, they should look Gaussian, basically, if you fit everything out that you would expect. Here's a case where they're really definitely not Gaussian. There's definite structure here with a period of about 1,000 days and something going on at 500 days as well. So one way you can deal with this, well, you know, you don't want to take a Fourier transform necessarily. You've got all kinds of funky sampling happening here, gaps in the data and things like that. What we actually did here was use something that comes from interferometry, the clean algorithm, and that can find periods as well. So the red line here indicates more or less the starting time of the data that went into this periodogram down here. And so this has a few peaks in it at 500 days, and then there's the equivalent thing at 1,000 days. And this could be getting into the regime of noise down here. The rough width that we're sensitive to here is indicated by this bar here. There's also a little bump there at 250 days, which shows up in other things in this, this pulsar. So just to go over how that clean algorithm works, basically you take the direct Fourier transform, so you can't necessarily do the fast Fourier transform here because of the sampling, but you can still compute a direct Fourier transform. It gives you what we call the dirty spectrum. And then you also compute your windowing function, basically by taking the Fourier transform of all the sample times, uneven as they are. Then you take your dirty spectrum and look for the highest peak in there and call that a clean component. You subtract that clean component convolved with the spectral window, but maybe you subtract only a fraction of it. So that's the gain in the clean algorithm. And you can keep doing this until you're satisfied that what's left is just noise. And then you can take those sets of clean components, convolve it again with a spectral window to acknowledge the width that you're dealing with. And that will give you this kind of clean spectrum. So as I said, this is an algorithm that's in constant use for interferometric map making, right? But you know, it was shown some time ago that it works quite well for 1D periodicities as well. Excuse me for a second. Another classic, which gets used a lot, is the Lohm-Skargel periodogram. So in a way, this is kind of like direct Fourier series fitting. So you fit a sinusoid at multiple frequencies, and then you take the chi-squared of the fit, and that gives you a periodogram here. So this is actually taken from the excellent documentation at the AstroPi website. Here's a set of samples. This is intended to be of a variable star in the optical. So your set of samples are here. If you run the Lohm-Skargel algorithm on it, you get a few peaks in the data here, right? And this line here is a calculated level of signal for which the false alarm probability is 0.01, so 1%. So things that stick up above this are things you ought to take seriously. And there's a really nice review article on Lohm-Skargel here. The signal here in the inset is folded at this frequency here, which is the highest frequency in there. But what are these other two peaks? They're actually aliases. So these are observations that happen about once per day. And so the this sets, the Nyquist frequency, if you will, in a way, but it also means that there's power at that 1/day period. And so it is possible for the observed frequency to be consisting of the true frequency, which we think is this one, plus or minus, that 1/day sampling period times some integer n, right? So that can be 0, 1, 2, etc. So these two signals here are from n equals 1, right? And -1 here and +1 here. So another point that's related to this is that you can, based on the sampling here, and it looks even weird if you have really irregular sampling, you can come up with something that sort of corresponds to the Nyquist frequency. But because some of your samples will be closer packed than average, you often have sensitivity to frequencies that are above the Nyquist frequency. So you have to be careful to cover a good frequency range when you're using this. Make sure that you're looking at everything you can look at. There's some care needed in interpretation of Lohm-Skargel, but it's quite a good algorithm. Here's another example of that aliasing, and this is bringing back that repeating fast radio burst that I showed early on in the talk. This was, well, we call it R3 at Chime because it was the third repeater discovered, and I actually had the honor of being on shift when the two bursts from it came in 10 minutes apart, and I realized, oh, this is a repeater. It showed up on my shift. And then we went back and found an earlier detection there as well, and then it started showing up regularly. So that was exciting enough, right? And then it turned out that they seemed to come in clumps, and Dongze Li, who's an enterprising PhD student at Toronto, tried to do a periodogram on this and realized that there was something there. There was actually a signal of 16.35 days. So what I've got up here is the set of Chime Detection. Sometimes there are 4 bursts that happen within a few days. Sometimes there's just one. Sometimes we don't catch it when it's on. Chime is, of course, a fixed telescope on the ground. So it's effectively a transit telescope. So we can only see things for a short time each day. There are detections at other telescopes along the way too. Effelsberg and LOFAR have seen it now too. But that's kind of interesting because it forces us to have, it means that our sample time or sample rate has a built-in aliasing issue of 1 over a sidereal day, right? So here's more or less the same equation we had on the last slide flipped around because this is the bigger number here. So it looks like we have a period of 16.35 days, but in principle that could be aliased, with some number n here. We argue that n is 0 for various different reasons, neither too large nor too negatively possible. I mean, some of it is just set by, we don't have appearances inside here. There are a couple of different arguments that we take, so you can go and look at the paper for the full set of those. But, the interesting thing is we didn't realize this. We didn't remember about this when we first set up the paper. And only after it had been out in the archive for a bit did people say, hey, you should think about aliasing. And we said, oh yeah, you're right. So that was a good reason for posting to the archive ahead of time. So I'm going to finish up this this talk with a little bit of what you can do to take advantage of the periodicity of pulsar signals. So we're kind of coming full circle a little bit. What I've got here is a couple of profiles from the double pulsar, A pulsar. So there's one pulsar where we see both of them, or did at some point see both of them. And to do pulsar timing, which is how we get all of our science, and how nanograv is getting its data and so on, we have to try to figure out exactly when this observed profile landed. So what we do is find a phase offset between this observed profile and what we call a standard profile. And this is built up by stacking many observations of the pulsar over time. And there are a few issues that go into that, as I'll get to in a moment. So these two profiles look kind of the same. As you can see, the observed one has more noise in it than the standard profile, right? So we're trying to determine this offset here. And of course, the easiest way to do it is just straightforward time domain cross correlation. But it turns out you can, whoops, how did that happen? Excuse me. That should not have happened. Don't know what happened there. Yeah, so to get a standard profile, I think, right, okay, we do have that. We build up the standard profile, adding up hundreds to thousands of pulsars. After adding up a few hundred, you'll get something that looks reproducible, like that individual observation. You probably want to add up many hours of data to get a standard profile, and I'll talk about that in a bit. Here we have another bright pulsar with a GBT, and every line is one single pulse coming from it. So you can see the huge variability here. But stacking up many pulsars does lead to a reproducible thing. So we actually do this cross correlation typically in the frequency domain, and this was another Joe Taylor brainwave. What this means is that we are taking advantage of the multiple harmonics that exist for a pulsar. So here we have one of my favorites, the double neutron star 1534 plus 12, rotated here so that its peak is in bin 0, just for ease of understanding the rest of it. So we have 1024 time samples across the profile. So 512 frequency bins, amplitude, and phase here. And so all of these samples out to about here can give you useful information for figuring out the cross correlation with an existing profile. So here's just a little math to show that. Basically, if we write the observed profile as some scaling factor times the standard with a time offset, that's tau. We take the Fourier transform of each side, then we write things where the k, the thetas and phis, and the k now represents the frequency bins. And then there's noise, and then there's a constant offset, which we're not going to worry about for now. And so to do this cross correlation, we're effectively minimizing this chi-squared here, where we're subtracting this quantity from that one. And you can work out what that noise is if you need to. This gives a very precise measurement of the phase offset, good to a 1/10 of a bin in the best cases, and that is how we get our timing precision of sub 100 microsecond timing for millisecond pulsars. So just a couple of issues about that standard profile as we finish up here. You only have the data that you can take to build up the standard profile. So you're forced to use existing data to do that. Now, it turns out there are a few things you need to worry about. If you build up the standard profile out of a whole bunch of low signal to noise observations, then when you take that same data and do that cross correlation with it, the noise will start to recognize itself and start to affect that shift that you measure. So here's a demonstration of that from the Australian group in Swinburne, where this set of profiles here was used to build up the standard profile, shifted normally, so they were perfectly aligned with each other. Then a shift was applied to a whole bunch of different simulated profiles here. And this is the phase offset that was measured. So you can see it's measuring a reasonable phase offset for the cases where the profiles were not incorporated into the standard. There's quite a lot of scatter. There's less scatter down here, and the values are wrong, right? And this is what happens with that Joe Taylor algorithm in particular in this case. So you want to be careful. You don't want to use too low signal to noise profiles, or that noise will, in the standard, will start to affect how you are measuring the offset. So using high signal to noise profiles is good. And then you can play some tricks with the standard profile as well. You can smooth it out either just by averaging things out, although that can tend to broaden things as well. There are some wavelet smoothing tricks out there that Paul Demarest came up with that work quite well. You can be brutal and have your profile and identify the baseline by hand and just set it to 0. That risks introducing a few high frequency things when you move from the baseline onto the pulse. Another trick that has been used a lot is to make an analytic profile by modeling the profile as a set of Gaussians. And that can do pretty well, but then you do have to worry about mismatch with the true profile values. So in my recent experience, I would say the wavelet smoothing actually works quite well. It's what we use in Nanograv as well. And then one more concern, and this is sort of leading to a whole new can of worms, which we will not get into, is the fact that pulsar profiles tend to evolve a lot with frequency. And then there's also a lot of scattering at low frequencies sometimes. And so to do things better, and we're starting to do this now in the Nanograv data, we're going to have to use two-dimensional fitting, or the two-dimensional version of the Taylor algorithm, of the Taylor algorithm rather, but using the frequency dependence of the profile shape. So the trick that is going to be modeling this well, right? So Tim Panucci's first attempt at doing this was to use Gaussians and allow their width and height to change with frequency, but that turned out not to be a great match for the data. And he now uses a PCA-based thing where you identify principal components with the frequency evolution and sort of fit for those, and you can do an analytic interpolation then of any frequency channels that you like. So this is a bit forward looking here, but it brings me to my last point. These are just summaries that there's still plenty of room for new and improved algorithms for dealing with periodic data, and hopefully some of you will contribute to those. I'll close by asking you to fill out that survey, which I think is going in the chat as well. And then I'll take a couple of questions. I've hit the time limit, I guess.
Thank you so much, Ingrid. This was really wonderful in terms of covering the various both issues that you face and many of the techniques that have been developed to search for periodicities. So we are open for questions. If you would like to ask something, you can raise your hand or put it in the Q&A or in the chat. And the link is indeed on the chat right now. We really appreciate your feedback. It helps us make our webinars better, more accessible, and in topics that are of interest to you. So we take the feedback seriously, so please fill it out. I have a question while we're giving everybody a chance to think about it. You talked about the coherent acceleration searches, and you listed several methods. When you're doing this for a source that hasn't been previously characterized, what do you do? Do you throw all of them at it at once, or how do you decide what you're going to do?
Yeah, so scoot back over there, I guess. Usually we pick one and use that. So what we use most of the time is, for like the P alpha search and so on, is the the frequency domain template-based search. So you're basically using a bank of templates to look for the spread in frequencies during your observation. That is completely equivalent to this one mathematically, and so there's no need to use both methods. This one up here can be done nicely in the case of something like a double neutron star binary, where you already know basically, because if you can measure enough parameters for that first pulsar, you sort of know what the orbit of the second neutron star ought to look like. And so it's easy to resample that over the course of an observation. And then it's a straightforward FFT search after that. So that tends to be the case where this one is used. The phase modulation search, we do that for long observations, but it's a separate running of the program, basically, on the d-dispersed time series. So, you know, it's a different algorithm. And this one, you know, it seems promising, but it's honestly not used that much. I think it's well suited to things where you have sort of half an hour or an hour of data at a time, and a lot of the more modern searches are shorter integration times than that, so we tend not to use it that much.
Great, thank you. I don't see questions, and we are at the hour, but if I can just ask one more thing before we wrap it up. You talked about PCA at the end. It's a technique that we're also using to characterize variability for EHT-related applications. Could you get into just a little more detail about how you're making use of it?
Okay. I'll go back over here to Tim's slide. So it's somewhat unfortunate because this comes from his earlier paper, and it doesn't show the PCA stuff. So there is a more recent paper, single author Tim Panucci paper from about, I think it's 2020 actually. So I would recommend that you go dig that up. But basically the idea is to look, so we're looking for principal components along the frequency axis, right? So the idea being that each of these frequency lines is a vector that we consider, and so we're looking for something that you know, we can bin it down a little bit if needed to bring up the signals to noise, but we're looking for, yeah, PCAs that describe the evolution. So the principal components 1 and 2. So 1 would just be the straight average of, you know, of the entire thing, and then you would see how many components are actually significant going, giving you evolution things in here. And then, you know, you can sort of, one of the things Tim does, which is kind of neat, is he plots one component against another connected as a function of a frequency. And so you can often see nice smooth curves there. So you have a bunch of measurements, and then you can try to fit some kind of spline to those to try to make a smooth thing that allows you to do a good interpolation afterwards. And so what happens then in the end for the fitting is that at each frequency channel, you're effectively having one of those Taylor equations, right? Except that you're fitting for a common shift. Where did it go? So you're effectively doing this, but now with multiple frequency channels, and where this tau is common to all frequency channels, right? But this SK here is going to be dependent on, it's going to be reconstructed from the PCA components that you've determined as a function of frequency.
Okay, thank you. All right, well, thank you everyone for attending, and many, many thanks to Ingrid Stairs for giving us this wonderful webinar. And the next one, thanks Ingrid. The next one, I can't remember the date, but there is going to be a next one in the series. Let me see, VLBI polarimetry techniques with Yvonne Marti Vidal on March 23rd. So hope to see all of you there. Bye.
Bye.